Got it.
So, hello everyone. Today we have Harshwardhan Reddy from TIFR Mumbai. He will present on the arithmetic of elliptic curves. First, you can start.
Okay. Today I want to talk about the arithmetic on elliptic curves. So my main reference will be Silverman and Tate's book. So it's a fairly elementary book. What I want to focus today is on proving the model-Weil theorem, which is that the arithmetic points, the rational points on an elliptic curve are finitely generated. So let me just start by talking about why do arithmetic on elliptic curves. So in the case of so arithmetic basically is about solutions of Diophantine equations. And in the case of one variable, we know by high school mathematics that the rational solutions, like the numerator will divide the an and the denominator will divide the a0. So there are finitely many and we can find them. So in two variables, the locus of the equation is a curve. And if you try to find solutions on a line, so let's start with some fixed point x naught y naught in the plane and with a rational slope n. Then the roots will be the roots which lie on this line and which lie on this curve will be the roots of a polynomial p whose quotients are rational, and it's the polynomial's degree will be basically the degree of f. And if f has degree 2, you have a conic, and the conic solutions can be parameterized by if you start with one given point in some number field, the other points can all be obtained by taking lines with slopes in k. And if f has degree 3, this is the case that we're interested in. So this degree 2 conic is basically genus 0, and for degree 3 cubic, we have two roots because you're starting with one root, and the other two roots of the polynomial, which will be a 3-degree polynomial, will be will give you you're starting with two given roots, and the third root will also be
rational solutions always exist.
This polynomial p will have degree 3, and there might be repetitions. There might be multiplicity. So I'm counting with multiplicity. Like if assuming that two of the roots are in k, the third root, because the product of the three roots is a constant term of pt. It will also be in k, assuming two of the roots are already in k. So we know that any genus 1 curve with one point and characteristic not equal to 2 or 3 can be expressed as solutions of a cubic in Weierstrass form. So I'm not going to prove this. This is actually non-trivial. It follows from Riemann-Roch. But assuming this, we can think any cubic can be written nicely as this in this format. And this equation is non-singular precisely when this right-hand side term here, the polynomial in x, has distinct roots. So, okay, so let me define an elliptic curve. It's a non-singular cubic with a specified base point. This base point will be the identity for the group operation. Okay, so why do arithmetic on elliptic curves? So the variable one variable case is trivial, and when you have a conic genus g equals 0, you can get all the points by looking at rationals by looking at lines starting from a point which is already on the conic and has slope in the number field. When genus equal to 1, we have our elliptic curve, and for genus higher than 1, we have a theorem of faulting, which is very recent, 1983, that there are only finitely many solutions over any number field. So the interesting case in some sense is genus g equal to 1 for elliptic curves, and there the solutions will be z to the power of r plus a torsion group. So we call r as the rank of the elliptic curve. Okay. So I'll just mention a little bit of history. Diophantine, whose name is the origin of Diophantine equations, already had a problem of elliptic curves in his problems on arithmetic. There was a problem posed by a Roman emperor of finding a right angle triangle of area phi, and Fibonacci won that challenge, I think. This is the congruence number problem. So xy by 2 is equal to 5 and x square plus y square is equal to a rational number square. Now that is, you can reformulate it by changing coordinates as an elliptic curve. And there was a, in 1621, Bakke found a duplication formula for this equation here. So basically, given a solution in modern terminology, he calculated 2 times p, like where 2 times p is the group law that we're going to talk about. So I guess you guys know more about the history of this subject. So maybe if you know more about it, you can mention it. Like if there are any other work which has been done on this. Okay. Okay. So so this is a geometric description of finding the third point. So if you have P and Q, you draw a line through the elliptic curve, and the third point, I'm calling it P star Q, but this is not actually the group law. The group law will be the inverse of this point P star Q. So all these pictures are from Silverman and Tate. Okay, so the group law. So this is a pictorial description of the group law. I'll give a explicit formula soon, but pictorially this is what it indicates. So you start with 2 points, you find the third point, and suppose you fix some point O on the curve, which we think of as the identity, and then you connect O to P star Q to get P plus Q. So P and Q P gives the third point P plus Q. And so typically you want O to be at infinity. So if you take the projective plane, I didn't mention it, but there is this elliptic equation has a point on the at infinity where where it basically becomes x cube equal to 0 after you projectivize the equation. So you have a point of multiplicity 3 at the infinity. So point of multiplicity 3 basically indicates that the identity plus identity is equal to identity. So if we push the identity to infinity, then after we take P and Q and get P star Q, the point from infinity connected to P star Q just gives you a straight vertical line, and you get P plus Q as a reflection of P star Q. So this is the group law pictorially, and you can also see the group law properties pictorially. Like suppose if we take this as the identity, if we take O as the identity, then P star O will be here, and this essentially shows that P plus O is equal to P. Because again, when you connect it, you come back to the same point. And similarly for, I think this was a negative. Yeah, this is a negative. Find the inverse. And the associativity is a bit complicated pictorially. But the good thing is that we have an explicit description of the group law. Given 2 points, x1, y1, x2, y2, we take a line through them, y equal to mx plus k with this slope, rations with this slope, and the constant is determined by these 2 points. And to get a third point, we just plug it into the cubic, and you get an explicit formula for the third point of the intersection, x3. And again, we have to be careful in the sense that y3 is not exactly going to be our sum of x1, y1, x2, y2. You have to reflect it, so to get x3. So this gives you the third point. And okay, so now the question is, what do the points on the elliptic curve look like? Are they finitely many? Are they infinitely many? Are they finitely generated, infinitely generated? So I think Poincaré already in 1901, he conjectured that the number of points on the elliptic curve, so this will be a group. And so to verify it's a group, you just have to do some simple checks with this explicit formula. So assuming that it's a group, now is it going to be a finitely generated group? So Poincaré conjectured that it was finitely generated group. And while, Mordell in 1923, he actually proved this. I think while generalize this to arbitrary number fields, I'm not exactly sure what the exact generalization, but it is true that the group of not only the group of rational points, but the group of points on in any number field is finitely generated. Okay. So this is the main theorem that I'm going to be looking at today. Like I'm going to look at the details of this. So let me just outline the proof. So already in Fermat's time, people were using the descent arguments to study solutions of like for instance x cube plus y cube equal to 1. Fermat studied that using the descent argument. So and that will be a crucial ingredient of our proof of the model-wise theorem. So obviously for a descent you need some notion of some bound of some quantity which is decreasing. So we'll call that the height. So we will use height bounds, and the heart of the proof is actually showing that so E is the elliptic curve. So and you can think of 2E as the doubling of the group, and we have to show that 2E has finite index in it. So this is the main essence, main part of the proof, and expressing the map x to 2x. So the way we do this is we want to show that this map x to 2x has finite co-kernel. So what we do is we write it as a composition of two maps, C and C, with finite co-kernel, and that will show that this map has finite co-kernel. And how do we show that these two maps have finite co-kernel? We explicitly identify the co-kernels of these two maps as finite subgroup of this group here, the space of
rationals.
Yeah, rationals modulo the square slash. So can you repeat your question again? Sorry.
Q star means non-zero rationals.
Yes, exactly. Q star is non-zero rationals. Non-zero rationals modulo the squares. Okay. So let me start with the height. So we want to do a descent argument, and obviously we need a height for that. The height of a rational number is just you write it in relatively prime terms, and you take the maximum of the numerator and denominator. So that's simple enough. And for a point on an elliptic curve, we can define the height as the height of its x coordinate. Okay. So you might be wondering why I'm ignoring the y coordinate, but the point is that the y coordinate is determined in terms of the x coordinate, and we'll soon see that you can get bounds for the height of the y coordinate in terms of the height of the x coordinate. So basically, we're not losing much information when you say h of p is equal to h of the x coordinate. And this height, capital H, it is multiplicative. Like for instance, if I take a rational and do h of r square, m square by n square, it multiplies, right? But so that's why we take the logarithm so that the small h becomes additive. So that's what I wrote here. But note that the height of R1 and R2 is in general is not equal to h of R1 plus h of R2, but it's less than equal to, because the point is when you multiply two rationals, there might be some cancellation which happens, and that cancellation can lead to problems in the sense that the height drops. So ideally we would like the height to drop, but sometimes we need lower bounds on the height also. So that sometimes complicates our proofs. But in any case, we know that the set of all rationals below a given point, below a given height, is finite, because there are only finitely many integers with numerator and denominator less than a given height. And that also says that the set of points on the elliptic curve below a given height is also finite. Why is that? Because clearly there are only finitely many x coordinates, because we are bounding the height of the x coordinate. But remember that the elliptic curve was given by y square equal to something, something, something. So for any fixed value of x, there are precisely two values of y. So if there are only finitely many values for x, there'll be 2 times that finitely many values for x, two times that finitely many values for y. So in total, there'll be finitely many values for on the curve. So that shows that the points in a given ball are finite. Okay, so now we would like to prove a translation bound. So P0 is some fixed point on the elliptic curve, fixed rational point. And we want to show that h of p plus P0 is less than equal to 2 times the height of p plus some constant. So translating by some fixed point on P0 will at most increase the height by 2 and some constant. So the third thing that we would like to do is, so we've done translations here, we want to scale. So if we scale the point by 2, the height increases by 4 up to a constant. And finally, this is the part I was mentioning, that
So this P and P0 both are rational or non-rational or what?
Yeah. So P0 is a rational point. Yeah, P0 is some rational point. I should have said that. Did I not say that? Yeah, I'm sorry, I should have said that. Yeah. So P0 is a rational point. So translating by P, so because we are looking only at the group of rational points lying on the elliptic curve. So we are looking at the subgroup of that. Okay. And we want to show that that group is finitely generated. So yes, P0 is a rational point. The index of, sorry, this is 2 times CQ, not C of T2Q. That doesn't make sense. 2 of CQ. Sorry. So the doubling map has finite co-kernel. That's another way of saying it. Okay, so these 4 properties, basically, they themselves, once we suppose we've shown these 4 properties, that will show that the group is finitely generated. The reason is that's the descent argument, which I'm going to describe this now. We want to translate any point. So suppose we start with any rational point on in the elliptic curve, and suppose it already lies on the double group 2 of CQ. So that means we can half the point, and halving the point basically decreases the height by 4. So this point has 4 times the height of this point up to a constant. So if we already lie on the double of the group, you can half the height by taking half. Sorry, you can decrease the height by 4 by halving the point. And when then we iterate it, we will end up in a bounded neighborhood which will be finite. But suppose we don't, suppose the point is not already inside this double of this group. So what we do is we use the fact that this group has a finite index, and there are only finitely many representatives of the cosets, and we can translate by one of the elements of the cosets, precisely the coset in which the rational point is lying in, to end up in 2CQ. So if a point doesn't lie in 2CQ, you can use finitely many representatives to land in 2CQ. So that will be a translation. So we're doing a translation to end up in 2CQ, and then we are doing a scaling to decrease the height by roughly 4. Yeah. So that's what I said here. Yeah. Okay. So so basically, this 2.1 instead of 2 is to basically to get rid of that constant, assuming that my point is sufficiently far away from the origin. That 0.1 of the height will be greater than the constant. So the translations will always be less than 2.1. And similarly for, yeah, this is basically what I've seen here. And similarly, 3.9, basically we can decrease the height by 3.9 outside some large enough halving. The operation P goes to half P, assuming that it's well defined, will decrease the height by at least 3.9 outside some finite ball. The 3.9 instead of 4 is basically to get rid of that constant. So we are doing 2 operations again. We are moving to the double group by a translation, and there are only finitely many points, so that the translation constant is bounded, and then we are halving it. So basically, the translation will increase the height by 2.1, and the halving decreases the height by 3.9. So you end up in a ball which is whose height is 2.1 by 3.9. So you're shrinking it by that constant C, C equal to 2.1 by 3.9. And we can keep on iterating it until we end up in a finite ball. And once we end up in the finite ball, you can pick the generators as essentially all the elements in the finite ball, plus the generators which you're using to translate. So the translation operation is basically all the cosets. So basically, the total number of elements in that finite ball plus these coset representatives P1, Pn, they will generate the whole group. So that's the proof that the model that the elliptic group is the rational points on the elliptic curve are finitely generated. So this is a descent argument. So the only thing that we need to do is to prove these bounds, like the finiteness we've shown, that's true. So we have to prove this translation bound, the scaling bound, and the index is finite. So this translation bound to prove that it's basically a computation, and like showing that the height is bounded, has the upper bound is not so hard, but showing the height has a lower bound is more non-trivial because of cancellation phenomenon. So let's just go through the proof. So the translation bound h of p plus p naught is less than or equal to k naught. So firstly, what we do is we bring any point on the elliptic curve can be brought into this format. Oh, sorry, this is n over e cubed. This should be n over e cubed. Okay. So what we do is we plug in take any rational point and we plug it into this formula, and then we clear denominators and we make a simple divisibility argument. So basically, once you get that m divides n square, you go back into that equation and again check it, and again you get a better bound, and you keep doing this, and you also use the fact that m and m, capital M, are relatively prime, and n and capital N are relatively prime. So you do a simple divisibility argument to get that we can make the denominator. Sorry, was there a question? Okay, so we can do a simple divisibility argument, show that the denominator capital M is of the form e square and the n is of the form e cubed. Okay, although the height of the point, so as I was saying earlier, the height of the point on an elliptic curve was just defined using the x coordinate, but we can also bound the y coordinate. So already we've got a bound for the denominator of the y coordinate, which is e cubed in terms of e square. So we can we got a bound on the denominator, but we can also get a bound on the numerator of the y coordinate. So again, you substitute the equation into the curve, like so you solve for n and you get that it will be the height of the point p. So in terms of all this, you get height of p times 1.5. Okay. So now, so this is the main part of this translation proof. To bound the height of p1, which is p plus p naught, we can use the explicit rational function. So remember that in the beginning of the slides, we had an explicit formula for the sum of the group law. So we use that, and we basically, if you do the computation, you get that it will be the coordinate of p1. The sum will be a rational function, and here we can substitute x is equal to m over e square and y equal to m over e cubed, and you can go from that formula to this formula here after clearing denominators. And the formula for the x coordinate is this, and basically you use the fact that m square. So the height of m square will be, for instance, it will be 2 times height. I'm taking the logarithmic height here, and the e has height p to the power of half, because e square was the denominator. So this is the square root of the denominator, so it will have 0.5. We already said n has height roughly proportional to 1.5, and m obviously has height less than height of the point itself. So doing all this, and we look at the each term in the denominator. For instance, take n. N has 1.5 height and e has 0.5 height. So this has height 2. So all the terms in the numerator have height 2. So e to the 4, for instance, e has height 0.5, e to the 4 will have height 2. And similarly for the denominator, all the heights have 2. So e square has height 2 and e4 has e square has height 1 and m has height 1. So this is height 2 and this is also height 2. So basically the upshot of all this is that we get that the height of p plus p naught is less than twice the height, because all these terms have height 2. Okay, so now we go to the scaling bound. Unlike the translation bound, this is non-trivial, okay, because of the cancellation phenomenon I said earlier. And so the explicit formula for, so when we plug in the, suppose the elliptic curve is y square equal to fx, where fx is equal to x cubed plus something. And we plug in the formula for 2p, like x plus, we have p plus p. and we take the x coordinate of 2p. So this is x2 is the x coordinate of 2p. You get this expression here, f prime x minus this something times f of x upon f of x. So remember that f of x is basically y square equal to fx, the fx which appears in the y square equal to fx, which defines the elliptic curve. And the elliptic curve is non-singular precisely when f doesn't have a repeated root, which is the same thing as saying that f and f prime are relatively prime. So that would imply that there are no common terms. The GCD of the denominator and the GCD of the numerator is 1. Yeah, because the elliptic curve, we are assuming it is non-singular. So that would imply that you get the x coordinate of 2p as some quartic polynomial divided by a cubic polynomial, and the numerator and denominator are relatively prime. Okay, so now we can reduce the bound to the following statements about arithmetic, a purely arithmetic statements. If phi x and cx are integer coefficient polynomials, which phi x and cx will be basically these, and d is the maximum of their degrees. So then there is an integer r independent of x, so that the GCD of phi applied to, so this n to the d here is basically to clear the denominators. So for us, phi of m to the n will be this numerator x to the 4 plus something something something, and phi of m to the n will be 4x cubed plus something something. So I'm multiplying by n to the d to clear the denominators, and the point is that after you do that, the GCD will be divides r, and this r is independent of m and n. It only depends upon the polynomial c and c, so it doesn't depend upon the point. So this basically ensures that the cancellation is not too bad. The cancellation can be at most r, and then the height of phi of over c has bounds. So using A, you can get a bound for the height of phi or c because the cancellation is bounded, and this is the equation that we're interested in. The upper bound is anyway not needed for us. We just need this lower bound on the height, and for us the degree of the numerator was 4, and d was a maximum of 4 and 3, so d will be 4 for us, and so we get the bound that we wanted, h over 2p is greater than or equal to 4 hp, because here d is equal to 4 for us. So the proof of this is basically not so hard, although I'm not doing it here. It's basically you plug it, again you do the same argument that we did for the previous case, and you get like some repeatedly, you have to do a recursive kind of thing, but you take this and you go back into the equation, and you keep on doing it until you get a bound for the GCD, and then you use the GCD to show that this is okay. So, but this is a purely arithmetic fact, and the point is that once we know this, we have a d equal to 4 as a we take d equal to 4 and we get the scaling bound. So we proved that, I mean, up to this fact here, we proved the arithmetic and the scaling bound. And now we have to show the important part of the proof, which is that the double of the group has finite index in the ambient group. So the way we do this is, so basically you can parameterize an elliptic curve as the complex numbers modulo a lattice. So suppose this is a fundamental domain of our elliptic curve. What I'm going to do is I'm going to define a map phi from this elliptic curve to another elliptic curve. So this will be my second elliptic curve, which has fundamental domain in this shaded region, half of it. So I'm going to define phi from here to here. And then the second thing that I'm going to do is I'm going to define phi from here to here. So it goes from here to here. But this new elliptic curve is basically the same elliptic curve reparameterized. I'm just decreasing the the omega 1 and omega 2 by 2. So this elliptic curve will be a reparameterization of this curve. So I'm going to call this initial curve C. This curve will be C bar, and this curve will be C bar bar, which is isomorphic to C. So that's what I'm going to do. So this is basically motivation for what I'm going to do here, which will be a bunch of arbitrary looking formulae. But the basic point is that we're going to do these two things. So assume that C has a rational point, which you can translate to 0 without changing the group structure. Then okay, so this is actually one thing which we are cheating a little bit, because so I'm assuming that y square equal to f of x. This f of x has one root, has a rational root. In general, y square equal to f of x is a cubic. It need not have a rational root. It will have a root which sits in a degree 3 extension of Q. So we have to do this whole proof over a degree 3 extension of Q, and we have to show that the ideal class group of that number field is finite, and we have to think about its group of units. So basically, there's a lot of number theory involved. If you don't assume that the f of x has f of x doesn't have a rational root, but if it has a rational root, we can translate and bring it to 0, and then you can there's no constant term for f of x, so the equation will look like this. Yes. So there's a little bit of loss of generality here. So I'm only proving it for elliptic curves y square equal to fx, where f of x has a rational root. Although the theorem is of course true even without that case, even without that assumption. Okay, so we define a new curve C bar, which has this equation. I'm changing the coordinates here, ax square and bx, like this. To instead of a, I have a bar, and instead of b, I have a b bar. So okay, and so I wrote this wrong here. It's x cube plus ax square plus bx. So sorry about that. Okay, it's x cube plus ax square plus bx, and the conjugate equation will be x cube plus a bar x square plus b bar x. Okay, so the curve has a geometric description in terms of the lattice description. So this is the point I was saying earlier. This curve C bar is basically half of omega 1, and omega 2 is omega 2 bar. It's the same thing. So although we won't use that, we don't need that for the proof, but that's basically where we're getting this a bar and b bar roughly from. We don't need that for the proof, but otherwise this is just some random looking formula. It's not so bad, but the map phi will be kind of arbitrary. So a bar is minus 2a and b bar is a square minus 4b. And then we look at C bar, and again we apply the same operation with the same thing. But now minus 2 of a bar will be 4 times a. So I get 4 of a. And a bar square minus 4b bar will be 16b. So we get this as the equation for C bar bar. So this is a scaled version of the original equation with x going to 4x and y going to 8y. Okay. So like I said, now we want to decompose the doubling map as C times phi. So phi goes from C to C bar, and C goes from C bar to C bar bar. And so the map we define from C to C bar is this this equation here. X bar is x plus a plus b by x, and y bar is this expression. The point is that once you take these expressions, so the point behind these two expressions is that once you take these two expressions and plug it into the equation of for C bar, you get that it will be a point. So a rational point for this equation goes to a rational point for this equation under this map. Xy goes to x bar y bar. So that's the point of these two formulae here. And obviously, the point of infinity, we can't define it using this way. So we define it as the point at infinity goes to the point of infinity, and t, where t is the origin, and the origin we can't plug in this formula because the x equal to 0 will give you an infinity. So we define phi of t again as the infinite point. So there are 2 points which are going to go to O bar. So so this is a 2-to-1 map basically, and again we have an analogous map from C to C bar to C bar bar. and we use the same formula but with a bar and b bar instead of a and b, and the point is that you can just do the computation to check that a point in C lands in C bar. That will prove automatically that a point in C bar will land in C bar because it's the same calculation. And these two explicit maps also are, if you can use the explicit group law, the explicit formula for the group law to and check that it's a group homomorphism. And the kernel is so the kernel is basically all the points which go to infinity, and none of these points go to infinity except the infinite point itself and the origin. So the kernel is just going to be this, and again the explicit calculation will show you that phi of C is equal to 2p. So all this is just calculation. Maybe there's a conceptual proof for this, but at least you can check this by calculation that these two maps are group homomorphisms and their composition is a doubling map. Okay, so now we have two maps, phi and psi, and we have to show that their composite has a finite kernel, and we use a simple fact about group theory that if you have two group homomorphisms, each of which has finite co-kernel, then their composite also has finite co-kernel. And the proof is very simple. Like you have, let's assume these are two maps.
What is kernel of this psi map?
Sorry, say that again.
What is the kernel of psi map?
So psi is exactly the same. So basically, it's the same calculation. So again, the kernel of psi will be infinity and the origin.
Okay.
Yeah, because psi is defined exactly the same way, except that you're just applying bars to everything, but it's like defined exactly the same way. Okay. Yeah. So coming back, let's assume that we have two. So here I'm just working with any two abelian, not even abelian groups, any two groups and any two maps. But in this case, we are going to use phi is equal to this and psi equal to this. But this is true for any two groups. So suppose phi has finite, the image of phi has finite index. That is the assumption. Then psi of phi of that group will have finite index in psi of phi. So firstly, psi of G2 will be a finite index subgroup in G3, but psi of 5 will have finite index in psi of G2. Precisely because phi of G1 has finite index in G2. And again, we know that psi of G2 has finite index G3. So you have a group sitting in as a finite index group of something which itself has sitting in finite index in G3. So we get that psi of C of G1 has finite index in G3. So yeah. So basically what we have done is that we have expressed the doubling map as a composite of psi and phi. The main thing that we need to check, the main goal is to show that phi and psi have finite index. And because I haven't used anything about phi and psi, like basically if you check that psi has finite index, that will automatically prove that phi has finite index, because this map is not dependent upon any particular elliptic curve. Maybe it's even functorial in the elliptic curve for whatever that means. But so basically, to check that psi or phi has finite index, you can check that either one of them has finite index. The whole thing is if it's from some elliptic curve to a bar of that elliptic curve. So phi is going from C to C bar, and psi is going from C bar to C bar bar. So we'll just check that the image of psi has finite index. So let's just characterize which points lie in the image of psi. So when x is not equal to 0, the points which lie in the image of psi are precisely the squares of rational numbers. So by the way, all this x and y are rational numbers, and we want to look at points which lie in the image of psi. Psi is going from the rational points on C to the rational points on C bar to the rational points on C. So again, psi is going from the rational points on C bar to the rational points on C of C, and P bar belongs to the image of psi if and only if the x coordinate is a square of some rational number, and the origin will lie in the image of psi the b was the coefficient of the elliptic curve, if b belongs to cube r square, and the infinite point obviously lies in the image, because we said that the infinite point goes to the infinite point, so it will lie in the image, and also the origin goes to infinite point, so it's definitely in the image. So here's the main point, like a point is in the image if and only if it's square. So how do we check that? So suppose x is w square, then we can explicit. So suppose there's a point x bar which is the square of a rational number. What we do is we can use these two. We can define these 2 points explicitly. X1 is equal to this, y1 equal to this, and the second point is x2 equal to this and y2 equal to this, and these 2 points will map to a point whose x coordinate is x. So which is w square. So again, this is just a calculation, but by symmetry, the same result will hold for C. But this time, instead of B, you have to look at the conjugate of B bar, which is a square minus 4B. And okay, so basically, my point is that the upshot of this calculation is that so this is an important point. Like we can define a map alpha which goes from the group. So gamma is I haven't defined gamma, but gamma is the rational points on this elliptic curve. And here I'm taking the elliptic curve C bar, and and the map is just take the x coordinate. You just take the x coordinate, but you go modulo the squares, the rational squares. And this lemma is basically saying is that the x coordinate, if it's the kernel of alpha is basically all the points whose x coordinate is a square, and the x coordinate is a square precisely when the point belongs to the image of psi. So the point here is that an element, a rational point on the elliptic curve C bar, maps to the identity in this quotient exactly when it's in the image of C. So the image of psi is the kernel of alpha. So we've checked. So what we've done is we want to show. So again, let me just remind you of our goal. We want to show that the image of psi and image of phi, they have finite index. So what I'm doing here is that I'm looking at the group gamma modulo the image of psi. I want to show that this is a finite group, and what I've done is I've embedded into this group q star upon q star square. And now we need to check that this image is finite, because q star modulo q star square is an infinite group. So just embedding it here doesn't show us that this group is the image of psi is finite. We have to show that this image is going to be finite. Image of alpha is going to be finite. So how do we do that? So this is the theorem that is the number theoretical heart of this proof, that the image of alpha will consist of these 2 power n elements, where pi are the primes dividing b. B was the coefficient of elliptic curve, x cube plus bx square plus cx, x cube plus ax square plus bx. So b was one of the coefficients of the elliptic curve. So all these primes dividing b will give you only finitely many points here. Okay. So the image of alpha is finite, and remember that alpha is embedding this group into q star upon q star square. So that will show that gamma over psi of gamma bar is gamma bar over psi of gamma bar is finite, which implies that image of psi is finite. Okay. So the proof of this number theoretic fact is basically, again, you take any point on the elliptic curve, as we've shown it, you can write it in this form, and we plug it into the equations, and when we simplify, we get this expression here, n square equal to some expression in m and b and e, and we take the GCD of this. Suppose n and m had GCD 1. Suppose n and m had GCD 1. Then both of these will be squares. Suppose the GCD, sorry, not the GCD of m and n. Suppose the GCD of m and this other term here was 1. Since the product is n squared, then the GCD would be 1. So both of these would be squares, which would show that m and both of these, m and this are trivial points. So basically that would give that that the this point here, m over e square, is trivial. So but in general we don't know that m and this other term here has GCD 1. So let's call that GCD D. Then we just do divide by D to get a GCD 1. So n by D, and we divide both of these by the GCD by D. And so since the product is a square, both of these are relatively prime. And modulo q square, we get that m over e square is equal to m, because e square is a square, so m over e square is going to be m modulo q square. And m is basically equal to m over d times d. It's not even congruent. It's equal to m over d times d. And yeah, so the point here is that if D divides both of these, it also divides, so if D divides M and D divides this expression here, then so these two terms are already divisible by M, so D also divides this B e to the 4. And but we've assumed that in this expression that M and E are relatively prime. So if D divides B e to the 4, D also divides B. So that's the main point here. If that D divides both of these expressions, M and this, then D is forced to divide this B e to the 4, and hence D divides B. So the GCD will divide B, and so we've reduced the x coordinate of a point in gamma to an element which will be of the form. So basically, it'll be an element which divides B. So this will be an element D which divides B. This is D which divides B, and B. If you take the prime factors, the PI will be basically the prime factors of B. P1 epsilon 1, P2 epsilon 1, and we can take the epsilon 1 to be 1 or 0, because if it's P1 epsilon square, like 5 or something, the P1 to the 4 you can get rid of it because you're going modulo q star square. So the epsilon I will just be 0 or 1, and that proves that the image of alpha is lies in this finite set, and hence image of psi is finite. Sorry, the index of the image of psi is finite. So so that basically shows that phi and psi have finite co-kernel. So the composite, which is the doubling map, has finite co-kernel. So, and that checks the last assumption of the 4 assumptions that we required for the disentanglement. Okay, so this is the proof of the model Y conjecture roughly. So the one thing that which I skipped was which I didn't do in full generality, was the assuming that the f of x has a rational point. Otherwise, we would need a number theoretic argument to show that. So this is the proof. So any questions so far? Okay, so this is basically an arithmetic argument and an estimate argument. So for the short time that's remaining, I would just quickly mention some results, not prove them, but just quickly mention some results. So we've talked about points in elliptic curves, and we've shown that the group is finitely generated. But this was a rational point. So the question is, what happens when you go for integer coordinates? And so there's a theorem by Siegel which says that there are only finitely many points. So this is a non-trivial theorem, highly non-trivial theorem. And then instead of the Q, we can look at over FP. And over FP, we have a Hasse-Weil theorem, which is that the elliptic curve has p plus 1 plus ap points, and this error term, so ap has basically 2 times square root of p, is less than or equal to 2 times square root of p. So Birch, Swinnerton, Dyer, they use this error term to construct an L function, and the conjecture is that the order of vanishing of the L function at that point 1 is basically the rank of the elliptic curve. So yeah, so this rank of the elliptic curve there's a lot of research about this, because precisely because we do not know if the rank is bounded. So it's an open conjecture, open problem whether the rank of the elliptic curve is bounded or it's unbounded. I think 30 is the highest rank. It was this. I think no Elkies found an elliptic curve with rank 30 or 31, but we don't have higher ranks than that. Was there anything else here? Yeah. So yeah, and also while has these conjectures, wild conjectures in general for not just for elliptic curves, but any genus and any, I think, even higher dimension varieties. And the point is that a lot of algebraic geometry developed by Grothendieck and his team were essentially to prove the wild conjectures. So the wild conjectures will tell you the number of points over finite fields in terms of the genus of the geometric object. Okay. An estimate for the number of points. Yeah.
What is wild conjecture?
So I haven't mentioned it here, but it's basically wild conjectures. They give an estimate for the number of points of a variety in terms of the genus of the variety. So in the Hasse-Weil thing, I think here it's 2 times root of GP or something. So but G is equal to 1. So for the elliptic curve, so you get 2 of square root of P. But I think wild conjectures are more general than just for curves. I think they're for surfaces and high dimensions.
It still remains conjecture, huh?
No, it was true. So it was Grothendieck developed his motivation for his whole schemes and algebraic geometry was to prove this wild conjectures, and he proved like one of the wild conjectures, but the last one was settled by Delin. It was some analog of the Riemann hypothesis, and Delin finally completed that program and he proved the wild. Okay. So the point of this development of algebraic geometry for Grothendieck was to unify number theory and algebraic geometry and put them in a common foundations. So and that program was successful, and they proved the wild conjectures. So we can deduce estimates for the points over number of points over FP. That's a number theoretic fact using a geometric data of the genus of the group. And I just want to mention one last thing about Galois theory, the relationship of elliptic curves to Galois theory. So there's a the class field theory in Galois theory says that any abelian extension of Q sits in Q zeta n, and so there's a whole so zeta n are special values of this holomorphic function e to the power I pi I z. So any abelian extension will sit inside Q adjoint to f of f1 by n. So any abelian extension over Q sits inside the field generated by a special value of this holomorphic function. And Kronecker's dream was to do this for not just for Q, but quadratic extension of Q, for instance, Q of I. So an abelian, and for those, the elliptic curves come into the picture. Any abelian extension over Qi sits inside Kn, where Kn is the field generated by the torsion points of this particular elliptic curve. And again, these so that itself is interesting, that the any abelian extension sits inside Kn. That's an analog of class field theory over Qi. And but not just that, these points, this Cn is a, I didn't did I define this? Cn is a torsion points of C whose torsion divides n. So Cn is the points whose order divides n. So there will be finitely many of them. It will be Z mod nz cross Z mod nz. The reason it will be Z mod nz cross Z mod nz is clear if you look at the lattice picture. The torsion points will basically be, you take the lattice and you divide it by n, so you get n square points. So you get you divide the omega 1 and omega 2 by n, and so you get n square points sitting inside a fundamental domain. So yeah, so Cn is basically Z mod n cross Z mod n, and these points are again the special values of a Weierstrass function rho and rho prime. So the elliptic curve enters the picture here. And since the Galois group, so this is usually in a Galois theory course, we say that the Galois group permutes the roots of a polynomial equation, but it will also permute the because this elliptic curve is any elliptic curve is, if you define it using rational coefficients, it will fix the base field, so it will permute the points of the elliptic curve, and the other thing is that it commutes with the group action, because the group action was again defined by rational functions. So the Galois group commutes with the group law. So it takes the points defined over K to the points defined over K, and it's not
it is group law. Group action perhaps means group law, right?
Yeah. So the group acts on the point defined over K. So the Galois group acts on the elliptic curve defined over K.
Yes, certainly means by permuting its coefficients.
Yes, because the point is that the group law basically is a rational function. So if 2 points are inside K, a rational function of those points will also be inside K. Yeah. So I'm almost done here. So I'll just take one more minute. So in particular, so it will be an automorphism over the points defined over capital K. So in particular, it permutes the torsion points of whose order divides n, and hence we get a Galois representation from the Galois group generated by. I'm taking the field K to be the group to be the field generated by the torsion endpoints, and generated by the points means, like, suppose I take a point, I take its x and y coordinate, and I take the field generated by x and y as x and y vary over all the points in Cn. So since we've said that Cn is Z mod n cross Z mod n, we get a linear. Every element of the Galois group will be a linear automorphism of Cn. So we get a map to GL to Z mod nz, and so we get a Galois representation. And Sayre has proved that apart from some points n, this map is surjective. So there are two assumptions. The first important assumption is that C doesn't have complex multiplication. C doesn't have complex multiplication. A complex multiplication just means, so on any elliptic curve, you have a natural map P goes to 5p, 6p, P goes to np in general. And if it has any other automorphism apart from that, we say that it's complex multiplication. And we can prove that any other automorphism will be multiplication by a complex number, because basically you need a lattice to rotate and land back in itself, and that will be multiplication by a number which is not real. So that's why we call it complex multiplication. Suppose it has an automorphism which is not the scaling by integers, we say it as complex multiplication. So when it doesn't have complex multiplication, Sayre proved that this Galois representation is surjective. Yeah, so that's all I wanted to say about Galois theory, and yeah, so I'm ending here. Thank you. So any questions?
Thanks, Harsha.
Yeah.
Wonderful.
Yeah.
So Hesse-Weil function is just constructed for counting points on varieties, right?
You're talking about the Weil conjectures, or?
Hesse-Weil function.
Yeah. Oh, yeah. So Hesse-Weil is for.
Here comes a Hesse-Weil function, right?
Yeah, this AP, AP is that, and you can construct a L function with that, and that goes into, that is the input for the Birch-Newton and that.
I see. Anyone has any questions?
What's a good exposition of this?
Sir, I was also new to number theory, and I studied Silverman and Tate, which is it's an undergraduate textbook, so you can actually read it like a novel. And there's also a book by Silverman, which is which is a graduate textbook, and it does.
What is the title of the Silverman Tate book? Rational points on elliptic curve, right?
Yes, and it's an undergraduate book actually. And the graduate book actually does it in full generality.
And Silverman has 2 volumes on this topic.
Yes, and also like the model while conjecture is not just true for rational points; it's true for points over number fields, and it's also true for abelian varieties. Serre has this whole book called Lectures on the Model While Conjecture, and I think he does for abelian varieties also, like higher dimensional.
I see.
Yeah, but I basically followed Silverman and Tate.
Okay.
Yeah. So
Okay, thanks. If no one has any
Thank you.
question, let us thanks Harsha again.
thank you.
So I will be ending the meeting now.
Okay.
Thanks, Harsha. See you next time sometime.
Thank you.